Well, welcome to another of the data system seminars at University of Waterloo. Our speaker today is Graefe. A lot of us know Goetz very well, of course. He's been a professor and has worked in industry for many years and been involved with core database technology for a very long time. He's currently at Google. Previously, he was at HP and at Microsoft. He's very well known for his work on query optimization and transactions. And today he's going to talk about advances in transaction management. Goetz?
Well, thank you very much, Tamer. This is the first time I'm presenting over Zoom, so hopefully this will be problem-free. So the title I'm giving you here is not precisely the title I gave you in the announcement, but I want to talk about these three techniques, and then we'll get to a point where we add them up and see what it gives. So we're going to talk about locking and transactions. We are not going to talk about low-level locking, in the database world usually called latching. So we are talking about coordinating user transaction, not coordinating threads. And these locks are typically held for entire transactions. We are not talking about critical sections. So transactions, the definition for properties, the one we are most interested in today is isolation, isolating one transaction from another. We are not interested in read-only transaction, at least not much. We are much more interested in transactions that read and write within the database, and that have multiple reads and multiple writes in a database, and all together are supposed to be atomic. So our correctness criterion is serial execution. Something that's equivalent to serial execution is considered good, at least with respect to concurrency control. So concurrency, multiple user transaction, concurrency control, you have multiple user transactions at the same time, but each one of them sees the database as if it were a serial transaction, as if all the other transactions either happened before or after. So commonly the word serializability get thrown around, which means you're not only look kind of similar to serial execution, but you actually prove in a provable way enforce restrictions on concurrency such that you have provable equivalence to serial execution. And the common wisdom in the industry and in academia about this, and now you know it too, is if you use either locking or serializability, then you get poor performance and poor scalability. So I assume everybody in this talk knows that too now, and at least for the time being. So to illustrate some of the points I'd like to make, I'm going to use a very simple example. Here is a little table, and maybe it's sorted by employee number, and employee number also serves as our row ID. So I will not distinguish between row ID and employee number. And really the column first name is the one we care about most. And the only thing that's interesting about that is that they are distinct names, except they are also a few duplicates. So there's two employees with the first name Jerry in this little database. So if I build an index on first name, this is what the index might look like. Because it's a non-unique index, I might actually associate with each distinct key value account and a list of employee numbers. And the way I think about this when I want to think about concurrency control, I think not about the list of index entries at the top, but I think of a sorted sequence. So I shaded at the bottom are the index entries, and then between index entries I have gaps. So for example, if there were another Jerry with the employee number 4, I would insert that employee into this gap. And then the gaps here are a little bit more complex, but hopefully they are understandable. So if there were another employee, say employee number 12, whose first name is also Gary, I would insert into this gap. If there were an employee named Harry, I would insert into this gap. and also if there were an employee number 2, I would insert into this gap, and so on. So the gaps, of course, are not stored at all. What is stored really is only what's shown at the top box. But the way I think about it and think about sizes of locks, scopes of locks, I use the diagram at the bottom because that helps me think about it. Questions about that? In general, if you have questions, speak up, because I don't see if you add comments into a message window or something like that. I just see my little screen, so just speak up, please. So if this is all crystal clear, then let's come to understanding what the problem I'm trying to solve here. So the claim is that poor performance, poor scalability, the traditional understanding comes from locking, comes from serializability, but I claim it comes from false conflicts. So let's think about this in the context of an ordered index like a database B tree. Imagine I want to lock the value Harry. Harry would fall into this gap here. So that's shaded in the title row where Harry belongs. And then I really need to lock only this gap. That's all I need to gap to make sure nobody can insert Harry while I'm assuming there is no Harry. And traditional methods, for example, there is an IBM method widely used that actually, instead of just locking what's shaded in the title, locks as much as shown in this row. There is another method used in Microsoft products that locks as much as this. There is an HB design that locks pretty much exactly this gap, but there is also now a Google design that actually locks only a fraction of this gap. So you can see if the small lock size is sufficient, then having these large lock sizes obviously can lead to false conflicts, meaning it appears two locks actually do have a conflict, but in reality, there is really no conflict between these two transactions. That's what's called a false conflict. So we are going to talk about false conflicts. We are going to first talk about false conflicts in terms of lock sizes, like this picture illustrates, but then we're also going to talk about lock durations, like when do you acquire a lock, when do you release a lock, that type of thing. All right, so this is my agenda, a long agenda. We already knocked off 2 of these bullets. I'm going to show you we're discussing the traditional solutions for lock sizes, and then 2 more newer solutions. And I think that all will come together when we discuss the case studies. On the right column, we talk about lock durations, and finally we sum up. So let's dive right in. So IBM key value locking was shown in the top row in this diagram a minute ago. All I needed to get from this a table, which was copied from the published paper about ARIES key value locking, is that it is darn complicated. And it does funny things like if you insert something, it actually locks the next key, not the key you're inserting, but the next key. And it uses intention locks for data as opposed to just for larger issues if you know about hierarchical locking. And it does something called instant duration locking, which of course is not a standard component of standard concurrency control theory. So all I want you to remember, it's darn complicated and nobody can memorize this table or nobody can derive it on the fly. Maybe this is a better way to understand ARIES key value locking. The lock size, when you lock a key value, you lock all key values that exist for this key value, the index entries that exist for this key value, but you also lock all Jerry's that don't exist. So if somebody locks key value Jerry, that means nobody can either delete or insert any of the existing or the non-existing Jerry's. So basically the count of Jerry stays constant once somebody has acquired this lock. And in addition to all the Jerry's, existing and non-existing Jerry's, you also always lock the gap to the left of the value you are locking. So let's keep this in mind as our understanding of key value locking, IBM ARIES key value locking. The other IBM system that's also used, and I think some systems in IBM call them type 1 and type 2 indexes. This table is a heck of a lot less complicated, so we like that. And the lock, the object we are locking is actually a logical row. So we might lock something like a row identifier like 3, which means we lock the index entry for row 3, and we lock the entire gap to the left down to the next index entry. The problem, or one possible problem, is that if we lock row identifier 3, we actually lock row identifier 3 across all indexes. So if you have another index on zip code or postal code, you also lock, when you lock row 3, you lock this index entry that belongs to that row, and then the entire gap to the left too. Sometimes that's good, sometimes that's bad. So anyway, that's hopefully understandable how large each lock scope is in ARIES index management locking. The third traditional system is Microsoft key range locking, which is actually invented at Digital, but then a whole bunch of people moved from DEC to Microsoft, and some of this technology came along with them. Here, we actually lock only within a single index. We do not lock across multiple indexes like IBM ARIES IM does. And we also lock index entries. So when we lock this index entry, we lock this index entry and the entire gap to the left. Jerry 6, index entry, gap to the left. Mary 5, index entry, gap to the left. Again, this is all going to come together a little bit better when we do the case studies. Now, the IBM or the Microsoft design for this actually had some amount of distinction. You could lock somewhat independently an entry and the gap, but that then was made completely independent and orthogonal in what I now call orthogonal key range locking. So this design locks a key index entry and in a separate lock mode, the gap. And this design shows to lock the gap, not to the left, but to the right. But that is, a tiny difference. It has some reasons in the structure of the B tree with, node to node pointers and all kinds of stuff, but it's not really a big difference for our discussion here. So each lock that you acquire, each time you invoke the lock manager, you basically specify 2 lock modes, one for the index entry and one for the succeeding gap. So an XN lock means you lock the key in exclusive mode, but you don't lock the gap, the following gap at all. And that gives you the concurrency control right to modify an existing entry. You cannot delete it. You cannot erase it completely, but you can modify some non-key columns of that entry. Similarly, if you want to lock just the gap, but not the key itself, you can do that, and that gives you phantom protection. Phantom means something gets inserted and appears to you in your transaction as coming out of nowhere. So if you look for something, it isn't there, then if you look again, it should still not be there. So for example, if you do an index nested loops join and the first outer row has a certain key value, you look up matches in the inner input of the join, you don't find a match. Now, 20 rows later in the outer input, you might get the same join key value. You look it up again, and suddenly there's something there. That would be a phantom, and that shouldn't happen in a serial execution. So any concurrency control method that promises equivalence to serial execution must prevent such a thing to happen. Okay, and so this lock, key-free, gap-shared, is very good for phantom protection. Now, if you have this many lock modes, you say, how complicated is a compatibility matrix going to be? And it's perhaps a little big, but it's not complicated because you basically, 2 locks are equivalent if the 2 first parts are two locks are compatible if the two first parts are compatible and the two second parts are compatible. So let's take this field here. One lock holds a key exclusive gap free lock, and another transaction wants a key free gap exclusive lock. And because this exclusive lock and this no lock are compatible, this no lock and this exclusive are compatible, that's why these two locks are compatible, and there is an OK in this field. So this lock compatibility matrix, as I said, perhaps a little bit big, but still very, very simple. And it can basically be derived mechanically from the core lock compatibility matrix, which is really just these four fields. That's a classic lock compatibility matrix. And everything else in this picture here derives from that. So what does it do? What does it permit you to do? Orthogonal key range locking, as I said, two completely independent lock modes for the index entry and the following gap. And so you can lock the index entry, shared or exclusive mode. You can lock the gap in shared or exclusive, or you can lock them both together. Now, this idea of orthogonality between key and gap, we can not only apply to index entries, but we also can apply it to distinct key values. And so when we do that, we get the following. When we lock key value Jerry, we can either lock all Jerrys, the one that exists and the ones that don't exist, or we lock the succeeding gap after key value Jerry, or the combination. But orthogonal key value locking has two more tricks up the sleeves. First, we actually permit partitioning the set of values. So we take these row IDs attached to the distinct key value Jerry, and we hash them. And in this case, my hash function is very sophisticated, row ID modulo 4. So if I want to lock partition 3, I actually lock not only this entry, but I also lock partition 3 in this gap. Also in this gap, there is no 3 because there's only 4 and 5 in there, and also 3 in this gap. If I lock partition number 1, I lock partition 1 here. I lock partition 1, meaning Jerry with row ID 5. If there were such a thing, I would lock that, and I lock partition 1 here. So that was the first trick up our sleeves. We partition the instances of the key value that actually of a key value like Jerry that actually exists in our index. And we also partition the gaps. So for example, this gap here between Jerry and Mary, we can partition. So if I have a query like this, how many Larrys are there in my database? I take the value Larry, I apply my hash function, and then I actually lock only one partition. All right, so let's try to have all of this come together in a couple of case studies, and hopefully everything really becomes crystal clear then. Before we do that, let me show you what you can do using the partitioning. Imagine you have two key values in a B tree, 80 and 90, and nothing in between, just a gap. Now, using our simplistic hash function, just modulo 4, all the values that could be in this gap are listed here in 4 partitions. So those do not exist. They just could be, they would belong there. So if transaction 1 says how many rows are there with key value equal 88, that's of course 0, but we also need phantom protection, so we need to prevent anybody from inserting an 88, because that would disturb the consistency of our transaction 1. So what we do is we get ourselves a shared lock on partition 0, because 88 modulo 4 is 0, so we get a shared lock on this. Now, if transaction 2 comes along and says, I wish I could insert 87, well, the partition with 87 is actually not locked, and we can actually permit that. And you and I as humans, we look at 87, 88, we say they are different values. Those two transactions ought not conflict. And indeed, in this system, they do not. So what we do for transaction 2, we first insert an invalid record with 87 and also repair the locks for transaction 1. So now transaction 1 owes shared lock on partition 0 of this gap and also partition 0 of this gap. And then we go back to transaction T2 and say, okay, there is now a value T87. It has an exclusive lock on it for you. You can do with what you want. So now transaction 2 can actually turn this ghost record or invalid record into a valid record and thus complete the insertion of this row into this index. And we can play the same game again in another transaction. Here, transaction 83 is inserted. And so even though 83 and 87 started in the same partition, we actually can permit all three of these transactions concurrently. And if that looks a little complicated, yes, perhaps a tiny bit. But on the other hand, this here is the only serializable concurrency control method that even permits concurrency among these three transactions. All existing methods would basically say once transaction T1 locks the gap, then transactions T2 and T3 would be out of luck. So we actually have here more concurrency. Again, the theme throughout this talk today is we eliminated false conflicts. So case study. Imagine you want phantom protection for value Harry. This is the example from the problem statement. You need to lock this gap. ARIES KVL locks Jerry, the following distinct key values. ARIES locks area IM locks the row or the row ID 3. Microsoft SQL Server would lock this index entry, and only orthogonal key value locking actually lock really only what is needed. And so the high cost of serializable isolation is really that existing industrially deployed transaction systems lock much more than they ought to. And so the high cost comes from the false conflicts. If you only detect conflicts that indeed exist, then probably you want that, because if two transactions conflict, you really don't want them to mess each other up. Having finer granularity and more precise locking is what you want. And I think that's what really the cause of this belief that serializability or locking are terrible for performance or scalability. So this is case study for phantom protection. Let's do another one for equality. So you have the query says select the number of people whose first name is Jerry. So you need to lock all Jerrys, existing and non-existing ones, so no other transaction can delete or insert Jerrys to just, to mess up our count. So ARIES KVL, you only overlock a little bit. The next three system, you overlock some, and you actually need multiple lock manager invocations to acquire multiple distinct locks. Whereas in orthogonal key value locking, you get exactly the lock you need, no more, no less, in one lock manager invocation. So again, the high cost comes from many locks and false conflicts. If we extend from an equality query to a range query, so here we have a simple range small enough to fit on my screen. You again see that ARIES KVL does somewhat well, still overlocks a little bit on the left. The next three methods overlock and require more lock manager invocation than they really should. Whereas orthogonal key value locking would lock key value Jerry, including its succeeding gap here. And then it would also lock key value Mary, but without the succeeding gap, because we don't need it for the query.
Hi, Goetz. Can I interrupt and ask a question?
Please.
Yeah. Okay. So what is the limits on the granularity with which you can partition? Can you partition, like your example would partition it by 4? Can you do it by 1,000,000? I mean, obviously it depends on, I guess, what the values that could enter there is, but what are the what are the costs of making things more the partitions more granular?
Well, in the lock manager, you have to track stuff like that, right? So if you can track stuff like that in a single word bitmap, that's very practical and efficient. If you say, I need memory management to represent a long list and so on within the lock manager, you probably have gone beyond what you should do. On the other hand, also think about how much concurrency do you really need for a single key value or for a single gap. So probably if you get to 15, where today all you can get is 1, well, that's pretty good already, right? So if I basically get rid of 14 out of 15 false conflicts, probably I've solved most of my problem. So somewhere in that neighborhood is probably a good pragmatic compromise. Answer your question?
Yeah, great. Thanks very much.
All right. So after these queries, let's look at some updates. Imagine I want to update an index entry. Assume for now I don't want to modify the key, so the index entry stays where it is, but I just want to update some additional field in it. And again, you see that these prior systems lock a lot more than I actually need if I only need the index entry itself in exclusive mode. Orthogonal key range locking is actually the most precise. Remember, orthogonal key range locking locks an entry and the entire gap to the right. So it could lock this entry and the entire gap to the right. So for updates, locking only one entry like this one here is the most precise, whereas orthogonal key value locking actually locks a partition of entries. So for example, if this is a 3, you would look partition 3 in all these gaps. But still, imagine it's 4, imagine it's 15 partitions. It's still fairly precise, whereas the industrial deployed systems lock a lot more than necessary and therefore lead to false conflicts. So beyond update, let's look at a deletion. And the way deletion is actually implemented in real systems, you don't actually erase what's there. What you do is you declare it invalid, you make it a ghost, so you actually do an update. And so this diagram you see here is precisely the same diagram as on the previous page, because what the user thinks of as a delete statement is really execute more like this statement here. The record remains on the B-tree node as an invalid record, basically until some other insertion requires space. And when you need space in the B-tree node, then you look for ghost records that are currently not locked, and then you erase those at that point. So again, for deletions, you see that orthogonal key range locking is the most precise, and orthogonal key value locking is almost as precise. For insertions, you play exactly the same trick. You actually first insert a ghost, and then you let the user transaction acquire a lock on the ghost and make the ghost into a valid record. So again, we have actually precisely the same picture. So summing up on lock sizes, we get phantom protection, we get much fewer false conflicts as previous systems, and we get much fewer locks. So we actually have eliminated a lot of false conflicts by changing the size of locks. Now we are going to talk about changing the duration of locks. And so we're going to work ourselves to the right column. So to do that, I need this little picture, how I think about it. So a transaction has multiple phases. First, we do all the application logic that typically requires the most CPU effort. And once all the changes, insertions, deletions in secondary indexes and all that stuff is done, then comes the commit logic. First, we need to do whatever is required to prepare for the commit and actually decide whether we can and should commit. Typically a very short operation. Then we actually put a commit log record into the log buffer. So this is not yet, the commit is not yet persistent. It's just that there is a commit log record, and this commit log record has an address and a position within the recovery log. And with that, the transaction also has a position within a sequence of equivalent, within a sequence of transaction in an equivalent serial execution. So basically, we said concurrency control is about high concurrency, but every transaction experiences serial execution as if it were serial execution. And it turns out that the sequence of commit log records is actually the sequence that the concurrency is equivalent to. So that typically only takes a few instructions. So I basically put in 1,000 instructions on a 5 gigahertz server. You can take different numbers. It doesn't make much difference. Some concurrency control methods require then some kind of post-commit operation that's part of the commit logic. And when all that is done, then you actually force a commit log record into the recovery log on stable storage. And I put here in the timing of an SSD write, local SSD write. So if you look at these times, the hardening is by far the longest phase. If you write to an SSD, of course, if you write to a disk, it's a lot longer. The application logic is the second longest phase, and that's why those two phases are shaded, so to focus on that, whereas the commit logic actually usually is very short. And well, we'll see in a moment that traditional locking and lock acquisition and release logic leads to many false conflicts that we can get rid of. So in traditional locking, we actually acquire the locks, shared and exclusive locks, during the read phase, and we release them after the transaction is complete, meaning after the hardening phase is complete. What we want is basically no locks or only shared locks during both of those long-running phases, so that we actually have strict exclusive locks only during a short commit logic. So if we actually accomplish that, then in a traditional locking, I just added up these numbers. It would be 220.2 microseconds for a transaction that I actually hold these locks, maybe some different numbers, whatever way you calculated. Whereas if I hold my exclusive locks only during the commit, I might have them for half a microsecond. So I would have an improvement in lock enforcement durations by 1, 2, or 3 orders of magnitude. And it doesn't even matter whether it's 100x or 1000x, it's somewhere in that neighborhood. So if we reduce the lock holding times by that much, obviously, and we are not creating a erroneous behavior, then we have gotten rid of a lot of false conflicts. So let's see whether we can do that. So in 1984, there is a famous paper. It's actually not famous for concurrency control, but it's famous for hash join, and it was one of the 3 papers that year that introduced hash join to the world. They actually had a comment on concurrency control early lock release, and their observation was the following. In a traditional disk-based system with a small buffer pool and many buffer pool faults, most of the time is spent in executing the transaction application logic. Maybe you even have a couple of buffer pool faults while you're executing the transaction application logic. And then finally, you do one IO to do the commit log, to force the commit log record to stable storage. So most of the time is spent in the execution logic and then a little bit in the commit. And they, in 1984, postulated an in-memory database, and that then became practical and pretty much ubiquitous 30-some years later. So now the execution of the application logic, the stored procedure, is fairly short. Hardening on an external storage device takes much longer, like in the calculations we did one slide ago. So if you think about when and how you hold a lock and what that does to transaction scheduling. If all these three transactions require the same to lock the same thing, we have to wait for the first transaction to finish hardening before the second transaction can even start running its logic. So we basically run these three transactions in this kind of schedule. Whereas the proposal in 1984 was, once you have decided you will commit, we don't need to coordinate this transaction anymore with anybody. We know what the position in the equivalent serial execution order is. So we can actually release the lock and we can actually permit this execution schedule. And this actually is somewhat true, but not always. And so that's what controlled lock violation tried to fix about 10 years ago. So let's talk about different transactions. If transactions are read-only and run in snapshot isolation, they have no locks and no lock violations, no delays, everything is good. If you have read-write transactions, if these three transactions at the bottom are read-write transactions, this transaction, the second transaction, will write its own commit log record. So it will absolutely only commit if this log record and if this commit log record is in stable storage. So we don't need to worry about this transaction at this point reading a freshly updated database value before this freshly updated database value is actually persistent. Because if that freshly updated database value doesn't make it into stable storage because there's a system crash, then this transaction will crash with it. And so we are, no problem. This transaction will also be rolled back. So on the other hand, if the second transaction here were a read-only transaction, it would commit at this point and it would be done. It would report to the application. It's all committed. So
yeah, kind of. I might get a break to take a shower.
Okay, so maybe somebody needs to mute. So if the system crashes at this point, then this update will actually be rolled back, but this transaction being a read-only and not having a hardening phase would actually report this updated value that after the recovery doesn't even exist anymore. So basically, if the violating second transaction is a read-write transaction, it just does its commit logic, no problem. But if the violating transaction is a read-only transaction, then we actually need to carefully delay its commit until the freshly updated value that it has read actually is indeed durable and permanent. And the delay we are forcing and introducing is as long as the delay of writing a commit log record in the a commit log record for the first transaction. And this problem can occur and is easily solved with controlled lock violation, both in distributed situations and also in local situations. So basically, what controlled lock violation does, it guarantees correctness, but it also permits a schedule like this one where it actually remains correct. Whereas most today's systems actually would force this schedule. Controlled lock violation also works very well in two-phase commit. So the traditional lock retention would retain the lock from the beginning or from the first access to the completion of both commit phases. Early lock release, as proposed in 1984, would retain a lock through the first phase, but with controlled lock violation, you can actually not release the lock, but let others violate it, let others read recently updated stuff immediately after the application logic is complete. And so the lock would be weak during both of the logging and communication phases. So what does controlled lock violation give us? forget the optimistic concurrency control stuff. So let's focus on the transitional locking, where we acquire the locks during the read phase and hold the locks throughout the hardening phase. Now with controlled lock violation, we basically do not have these. I mean, in effect, we actually still have the locks, but in effect, in terms of exclusion, these locks don't do any damage anymore. So basically, the locks practically are absent during the long-running hardening phase of a transaction. So basically, we achieved one of our goals, that we basically have high concurrency during this long-running phase, during this longest-running phase of typical transactions today. So we got one step towards our research goal. Now, the next step will be to introduce deferred lock enforcement, which actually gives us a similar effect during the other long-running phase of a transaction. So how does it work? This on the top left is a standard lock compatibility matrix. Everybody has seen this, I like to believe. In short and exclusive locks, we also have update locks in many systems since the 1990s. So for 30 years, everybody has had update locks, I believe. And what an update lock is, it's a shared lock, so I can read something. But in addition to that, whoever holds the update lock is also first in line for an upgrade to an exclusive lock. So let's look at lock compatibility. Somebody holds a shared lock. Somebody else wants a shared lock. That's okay. Somebody holds a shared lock. Somebody else wants an update lock. That's also okay. The second transaction gains shared access, read access, and it gets to be first in line for an update. So that's okay. Now, if somebody already holds an update lock and somebody else wants an update lock, as far as reading, that's okay. But because now both transactions want to be first in line for anything, that doesn't work. So therefore, a second update lock is not compatible with the first update lock. But what if the first transaction holds an update lock and the second transaction only wants to read? Well, you could argue either way. You could say, well, the first transaction only has an update lock. It doesn't have an exclusive lock yet. So while the first transaction decides whether or not to indeed upgrade to exclusive, let the other reader proceed. So you could say yes. Or you could say, no, the update lock didn't get a shared lock because it really wanted to update. So don't mess that up. Don't make the update lock holder starve. So maybe you should say no. So this question mark, you could answer either way. And the people in SQLite actually said, we're going to make it explicit which choice we take. And we actually, instead of having an update lock, we have two lock modes, which they call reserved and pending. And they are basically both of those are forms of update locks. And you can see reserved and pending always behave the same with each other, except exactly where this question mark is. A reserved lock says, yes, another reader may come in, and the pending lock says no. And so the way they organized updates in SQLite is, while a transaction computes what it wants to update, it only takes reserved locks. But once this transaction has finished computing what it wants to update, then it actually upgrades all its reserved locks to pending locks. Pending locks now mean existing readers can finish, but new readers have to wait. And so once all the existing readers indeed have finished, then SQLite will upgrade its pending locks to exclusive locks and actually apply the updates. And we are going to do something very similar, but we are not going to do it only for files like SQLite does. But we are actually not going to have explicit lock modes. What we do instead in this design, deferred lock enforcement, we only have exclusive locks, and we acquire exclusive locks from the get-go. But the semantics of these exclusive locks depend on how far along the transaction is. So while the transaction is still in its read phase, we interpret exclusive locks as if they were reserved locks. When a transaction once attempts to commit, we interpret exclusive locks as if they were pending locks. And then when the pending locks actually have been converted to X locks, that's when we actually have exclusive locks on everything we need to update. And at that point, we actually apply the update to the database. Now, by making this dependent on the transaction state, we actually get the fact that multiple such exclusive locks do their transitions at the same time. So basically, by flipping the state in the transaction descriptor, all these transactions exclusive locks change their state from reserved to pending. And once they're pending, they're all waiting for the readers to finish and disappear, and then they become exclusive locks. And why is it useful to have concurrent waiting? Well, it's useful because most update transactions have multiple exclusive locks, either because they update multiple rows or multiple tables. But even if they only update a single row in a single table, they often will update multiple indexes. So most update transactions hold multiple exclusive locks. Upgrading these exclusive locks one at a time and waiting for readers to disappear one at a time would increase the commit times tremendously. By doing the concurrent waiting, we actually compress the time it takes to go through the commit phase. So what that gives us is exactly what we want, namely that while a transaction is still in its application logic, it holds exclusive locks, but they have the semantics of reserved locks, meaning they are perfectly compatible with existing and new readers, meaning transactions can actually run very freely, very concurrently. So we have very weak exclusive locks. The only thing that these exclusive locks do is they prevent others. Remember, reserved locks are two reserved locks by two transactions are not compatible, just like two update locks are not compatible. If we combine deferred lock enforcement and controlled lock violation, we really get, practically we get rid of exclusive locks during both the long running phases. So now we have something that looks very different from traditional locking. And we have gotten rid of a lot of false conflicts, but we can do better. And by doing better, we focus on write-write conflicts for a moment. In optimistic concurrency control, all checking happens at the end of transaction validation. And so that means optimistic transactions have to create new versions of the things they want to update, the rows, the index entries, in some kind of memory that is the write set or the transaction private update buffer, whatever your favorite term is. But in deferred lock enforcement, we actually find write-write conflicts immediately because two writers would both try to have a reserved lock or an exclusive lock in reserved semantics. And they can't because update locks and reserved locks are not compatible. So we discover immediately when the second writer attempts to become a writer, attempts to get the lock. And because we discover immediately when there is multiple writers, we can guarantee that for any one lockable object, there is only one uncommitted version because only one transaction can hold an exclusive lock, even if it's only in reserved semantics at that point. Which means we can actually put this one and only new version or uncommitted version, we can put it directly in its final location. Like if we write a new version of an index entry, we can just put the new version right next to the existing index entry, which is equivalent to saying we don't have a transaction private update buffer, which also then implies we don't need to do any memory management for the transaction private update buffer. We don't need to look aside. Like when I look something up in the database, in optimistic, I always have to say, oh, did I update this already? Do I have a newer version of this in my transaction private update buffer? We don't need that if we put the new version in its final location. And we also don't need any update propagation after the commit log record has been added to the buffer. So we get this picture that with multi-version storage, we don't have this update propagation anymore. We basically just put a new version that immediately in its final location, and it basically remains invisible there until it gets unlocked by the updating transaction. So now look at the duration of locks in transitional locking versus duration of exclusive lock in our modified design. So we eliminate both of the long-running phases, and we eliminate even one of the commit steps. So now exclusive locks really exist only for an extremely short period of time. The remaining concurrency constriction in this design is we cannot have multiple updaters for the same lockable object, which is a good thing because one of them wouldn't be able to commit. So, delaying or killing one of them early is better than killing one of them at the end, which is what optimistic would do. An updater cannot commit while there is still a reader relying on repeatable read. That's a good thing because it actually preserves repeatable read, repeatable count, which is what we want to preserve if we want to preserve the equivalence to serial execution. A new reader must wait while an updater commit, not a long time until an updater is finally done, but while an updater is actually in the commit logic, done with its application logic, really in the commit logic. A new reader must wait until that commit is indeed complete, but we saw that the commit logic is just fractions of a microsecond. And finally, if you read an update before that update is durable, meaning the log record is on stable storage, then you have to possibly delay your commit yourself a little bit, so you do not commit to reading something that actually never became durable. So those are the remaining restrictions, very weak restrictions indeed. So now if I compare this with optimistic concurrency control, even the most advantageous version of optimistic concurrency control still has a higher concurrency control footprint, more exclusion than what locking can be if we organize locking well. So now, independent of what your implementation is, we can guarantee that locking will have less conflict, fewer conflict than optimistic concurrency control, even the best optimistic concurrency control. What remains for optimistic to be better is cheating in various forms, like not providing phantom protection. And not providing phantom protection seems natural in optimistic concurrency control, because how do you put a timestamp on a gap? A gap means nothing is stored. So what do you do with your timestamp? Where do you put it? What do you attach it to? And similarly, if you do read set and write set, how do you put nothingness into your read set? Meaning, how do you put a gap into your read set? So most people just don't do it in optimistic concurrency control. So what we have now is we have worked on the sizes of locks. We have reduced sizes. We also now have reduced durations. We don't have read-write conflicts anymore in the long transaction forms, also not write-read conflicts. And we only have write-write conflicts that we want to preserve, or that we want to discover, so we don't have a transaction, two transactions where one of them has to commit. So let's summarize. We have worked on sizes. We have worked on lock durations. I think we now have the minimal period for strict exclusion with the combination of deferred lock enforcement and controlled lock violation. We could also further introduce additional lock modes, in particular increment decrement locks in roll-up, materialized roll-up views. And we could also work on lock acquisition sequence, which actually in a system like Microsoft SQL Server, they could get rid of 50 to 80% of their deadlocks by modifying the lock acquisition order. So coming back to what I started out with on the title slide, if we take these three techniques and we add multi-version storage, we get multiple consequences. Number one, we really have something that is categorically better than any optimistic concurrency control. But maybe more importantly, we could implement all our transaction and all our system as serializable transaction, because if you get rid of the false conflicts, what remains is the true conflicts. And I believe you don't want to throw out false conflicts if that means you also do not see true conflicts. I think you want to see true conflicts, and because that guarantees you that your transactions are actually correct. The way systems work today is not like this. Actually, both DB2 and Oracle and SQL Server, they all ship by default with a serializability level that is substantially weaker than equivalent to serial execution. And finally, all these techniques are good fits for two-phase commit. So that's also very nice because most systems nowadays are scalable systems. So for discussion, I just put up these two slides again for questions and discussion. Those basic two slides kind of summarize at the top lock sizes, at the bottom lock durations. So thank you very much for your attention, for your patience, and if you have questions, please.
Thank you very much, Goetz, for a very detailed, very nice talk. We have some questions. Anybody who has questions, please raise your hand or indicate in chat, and I'll call on you. Ida has a question. Ida, you can unmute, and if you want, start your video and ask your question.
Sure, thank you. I think you can see my video now, right?
Yep.
Yes.
Okay. Hi, guys. Thank you so much for your great talk. I learned a lot. It is because of my limited knowledge that I am going to ask this question. I was wondering if you could talk a little bit more about the workloads and the requirements that the workload may impose to the designing of solutions for lock management and stuff like that, especially because of with respect to the frequency of, for example, writes, reads, and updates. Because in the first part of your talk, when you were talking about how to do this lock management, you didn't focus on these type of things, but when you were talking about when to do the lock and for how long, and I mean the lock duration, you talked about this, and I wanted to pick your mind on these topics as well, and also about the impact of other parts of the database management system on these solutions. And do we need to take these into consideration when we design such solution, and how we can evaluate the solutions with respect to the workloads? When can we say, for example, this solution, I mean, you talk about different scenarios, but I mean, one solution which doesn't work in a specific scenario may work fine in given a specific workload. So what do you think about this? Thank you.
Okay, good. All right. So the big difference between building an application versus building a platform is, I think with an application, you typically know exactly what you want to accomplish. Whereas if you build a platform, you really have to be prepared for any workload, right? I mean, you building a file system that is only good for small files, or building a file system that's only good for large files, well, you kind of boxed yourself in. If you build a file system, you have to be able to deal with any size file. Similarly, if you build a database system that you want to offer as a platform for many applications, you have to be prepared to deal with small transaction, last transaction, many read transactions, many update transactions, and so on and so on. So what I was trying to do, both when I was talking about lock sizes, but also when I was talking about lock durations, was accommodate any workload. Now, in addition to locking individual index entries, you might also have even coarser levels of granularity. Those are fairly easy to implement. I mean, you lock an entire index, you lock an entire table. In SQLite, they lock an entire file at a time. Those are always perfectly compatible, and you're always free to use those if your platform is supporting an application and workload where that is sufficient. But then, of course, if you lock an entire file or you lock an entire index, you might very well end up locking much more than you need, and you basically have possibly false conflicts. You're holding back a second, a third, and a fourth transaction, even though there's logically no real, if you just think of it, look at it as a human, there's no reason to hold back these other transactions. Other system components you would be wanting to think about is for example, your index structure, your B-tree structure. I mentioned in passing that whether you lock to the left of the index entry or to the right of the index entry has something to do with the pointers among leaves in a B-tree. Yes, those little things actually also you need to consider. I don't think the methods I was describing or proposing impose any harsh restrictions on that. Similarly, you would be wanting to think about logging and recovery in general. And I think any of the ARIES methods would directly apply, but so would also all these methods that I described as instant recovery. They would immediately apply and be compatible. So I think these proposals are very generic and would fit a wide variety of workloads and systems. I hope that answered your question somewhat.
Yes, thank you. Thank you.
All right.
Paul Larson has a question. Paul, you can ask
Hi,
your
Goetz.
question.
Can you hear me?
Yes, hear you loud and clear, Paul. Good to see you.
Very good. So I was wondering about the cost of detecting these immediate write-write conflicts. So let's say that I have a transaction that has taken out, say, 50 exclusive locks, and now it wants to change mode. What does it have to do?
It wants to change what, please?
Mode. Transaction
From
state.
what? Okay, what you have to do is, so you have these exclusive locks.
Right.
The exclusive locks so far have the semantics of reserved.
Right.
All you have to do is flip one bit in the transaction descriptor. Now, the assumption here is that when a transaction attempts to acquire a lock and it sees another lock that might be a conflict, then that transaction has to actually go back to the holder of the existing lock and see what state is that first transaction in. So if I want to acquire a lock, I see you, let's say I want to acquire a shared lock, and I see you hold an exclusive lock already, then we might have a conflict. So now I have to go and find out what is your transaction state. If you're still in working state, meaning you're still in the application stored procedure logic, meaning your exclusive lock has the semantics of a reserved lock, then I can actually acquire my shared lock and proceed. Because you are nowhere near committing yet. When you want to commit, you just flip in your transaction descriptor from working to attempting to commit. Okay. Now, if I now come and want to acquire a shared lock, and I see that you are already attempting, right? Then I would not acquire the lock, because that gives you your exclusive locks the semantics of reserved. So in that case, I need to back off.
So the additional cost is that on lock acquisition, I actually have to go and check the state of the transaction, of another transaction.
Yes, if there actually is a conflicting lock or potentially conflicting lock, then I can go inquire about the holding transaction state, and then I make a decision to either block or to proceed.
Right. Okay. Thanks.
Was there one more question? I see a hand up, but I don't know who hand is up.
Yeah, if I may.
Sure.
I was wondering, now that you have found more or less the minimum critical section for a single transaction, where are you looking for further speed up? And especially, could be concurrency within a transaction be a reasonable place to look at?
Absolutely. If I have actually a partitioned database where partitions reside on separate nodes in a network, for example, on a cluster, then obviously I will have concurrency. I can play the same game within a single largish server. Of course, that only really pays if my transactions are of substantial size. If my transactions are debit credit transaction, you know, move $50 from this account to that account, probably there is limited opportunity for parallelize within that one transaction. So that's a fairly generic but an obvious answer. Other places for speed up, as I said, I would look at lock modes. In particular, if I have a materialized views that have group by in the view definition. Because for example, if I have a view like sum of salary by department, I might be modifying two employees. Those two employees have nothing to do with each other. So, but the only thing that they have in common, they happen to be in the same department, but I'm currently just modifying their salary, not their department membership, right? So now there's no conflict between these two updates. But if I have a materialized view, sum of salary by department, I need to increment that sum twice. And so now if I enable concurrently by increment locks, then I actually could possibly gain, depending on how much updates you have. So does it answer your question?
Yeah, thank you.
I think this is a good place to end. Thank you again, Goetz, very much for the talk.
Yeah, thank you all for your patience.